Welcome to the physics class for December the 10th. Let's go over the announcements first. All right, so the test rework, don't forget that that is a required assignment for everybody who got less than 100% on the test. And as I mentioned last time, there were quite a few of you that got 100% on the test. So that was great. So yeah, that is going to be due on Friday of next week. I'll just put it as midnight Friday of next week. So you need to redo all of the problems, even the ones that you got right. And also that very last problem, the one that was an extra credit problem on the test, well, it's not extra credit anymore. Everybody needs to do it. That's something that you should all know how to do. Now, if you need little help doing it, that's okay. Remember, when you do the test rework, it's okay to work together with your friends. I have no problem with that. Okay, and then tutoring. Remember that there's tutoring available on Tuesdays and Thursdays after school from 4 till 5. It's also available on Fridays from 11:30 to 12:30. And we've also added 2 new sessions on Saturdays. So Saturday from 11 till 12, and then also on Saturday from 4 until 5. So you have plenty of opportunities to get tutoring help. Make sure you take advantage of that. And I think that's pretty much it for the announcements. Let's go ahead and talk about last night's homework. Here, I'll share my screen with you.
For the test rework, will we be able to tell which questions we got wrong? So we know.
Yes. Yes, when you submit your answers, it will tell you what ones you got wrong. It won't tell you what the right answers are, but it will tell you what ones you got wrong. That is true. Okay, so here are the answers to last night's homework. As usual, if you could only see one problem worked through, please type into the chat box what that one problem would be. So I'm seeing a couple votes for problem number 24. Seeing a lot of votes for problem number 24. Okay, so problem number 24 is the clear winner here. All right, so that is definitely the one we're going to do. So that's the billiard ball problem, if I remember right. Yeah, that was it. Okay. Let me get this one. Sorry, I was in the wrong chapter there. Okay, so we got a stationary billiard ball hit by an identical ball after they move. Okay. All right, so let's open up the whiteboard. So Caleb is saying you thought you were skipping angular momentum. Yeah, we are skipping angular momentum. Okay. Okay, so what we have here is a billiard ball just sitting here minding its own business, not bothering anybody. Its velocity is 0. And along comes a very rude other billiard ball, which has the same mass and is moving at some velocity, v initial, which I think was 4, if I remember right. Yeah, 4. Okay, and so this is the before picture. All right, and let me switch to red ink for the after picture. All right, so afterwards, the ball that had initially been stationary is moving 30 degrees to the right of the direction where the incoming ball had previously been going. Okay, so this angle here is 30 degrees. That's the ball that had been stationary. And the ball that was originally moving, it is now going off here at an angle of 60 degrees. And we want to know what is the velocity of each one. Okay, so let's call this guy 1 and let's call this guy 2. So this is going to be V1 and this down here is going to be V2. And so our job is to find out what those velocities are. Okay, so hopefully you guys realize this is a collision. Whenever you have a collision, the equation you want to use comes from conservation of momentum. So that tells us that sigma p before the event happened has to equal sigma p after the event happened. Okay. All right. Now this is a two-dimensional problem. So that means we have to look at, we have to separate the x and y. And so let me put an x here and x here. So if we add up all the momentum in the x direction before, it has to equal all the x momentum afterwards. And the same thing is going to occur in the y direction too. So let's do the x first, and then we'll come back and we'll do this a second time in the y direction. All right, so before the crash, the only guy that has any momentum at all is M1, and all of his momentum is in the x direction. Okay, so that means that M now, and they both have the same mass, so I'm just going to call them both M, right? So M times V initial, that is our total momentum before the crash. Now, after the crash, we've got two guys who are both moving, so we're going to have two momentums. Okay, but it's only the x momentum that I want. So I've got some funky velocities here. Let's defunkify them. So let's break this guy up into his components. So this is going to be our x component. So I'm going to call this v1x. And this is going to be our y component. So I'm going to call that v1y. And by the way, let's go ahead and let's just put in. So v1x we know is going to equal v1 times the cosine of 60. And v1y we know is going to equal v1 times the sine of 60. And then we're going to do the same thing down here. We're going to say that v2x component is going to equal v2 times the cosine of 30. And the y component is going to be equal v2 times the sine of 30. Okay, so after the crash here, our momentum from this guy is going to be m times the x component, which is going to be v1 cosine of 60. But we also have to worry about the x momentum that comes from this guy. So I'm going to say plus here, but I don't have enough room, so I'll write it down below. So it's going to be his mass, which is the same m, that makes life a little easier there, times v2 times the cosine of whatever that angle is, which is 30. Okay, so here's one equation. But you can see we've got two unknowns. Now V1 initial is a known number, so that's good. And by the way, notice how the masses cancel out. So they told you what the mass of the billiard ball was, but it turns out you didn't need to know. As long as the mass is the same, it cancels out. Now, if the mass wasn't the same, then it wouldn't cancel out. But okay, so we got two unknowns. We don't know what V1 is. We don't know what V2 is. We got two unknowns, only one equation. Rats. What are we going to do? Well, we need another equation. Where are we going to get that other equation? From the y direction. What we're going to do is we're going to say sigma p in the y direction before the crash has to equal sigma p in the y direction after the crash. So before the crash, what have we got? Well, mass number 2 is not moving, so he doesn't contribute any momentum. Mass number 1 is moving, but he's moving in the x direction. He's not moving in the y direction. So before the crash, we have no momentum. But after the crash, we do. That's weird. How is it that we can have momentum after the crash if we didn't have momentum before the crash? Well, remember, vectors. Thank you. Yes, they are vectors. So one of them is going to be positive, one of them is going to be negative. They're going to cancel each other out. So let's define the plus direction be up. So then this guy here is going to give us some positive momentum. So that's going to be m times v1 sine 60. And then minus the other guy, because he's in the negative direction. So minus v2 times the sine of 30. Okay, so from this point on, it's no longer a physics problem. Now it's just a math problem, and you're good at math, right? Well, I'll tell you what, this one is a little bit of a tricky math problem. So rather than just calling it quits here, I'm willing to go ahead and do it. Okay, so we got two equations, two unknowns. Let's use substitution. All right, so let's take this bottom guy here. Let's add
the expressions here become worlds easier if you plug in sine and cosine of 30 and 60.
Yes, I agree. That probably will make it easier. I'm going to hold off. I will do it in about one step, but for right now, let's not. So I'm going to add a V2 sine 30 to each side. And so that what I'm going to get then is going to be V2 times the sine of 30 equals V1 times, and by the way, I forgot to put my masses in there. Shame on me. This is momentum, not velocity. So see that mass that I just wrote in there? Yeah, that needs to go in there. And then once I do that, then I see that each term has an m in it, so I can cancel them out. Okay, so the masses are now gone. So V1 sine of 60. And so then what I get is, let's solve for V2 and then we'll plug that in. So V2 then is equal to V1 times the sine of 60 divided by the sine of 30. And now I think would be a good time to take Luke's suggestion. Let's put a number in there. You know, normally I like to do the algebra using the letters, not the numbers. But right now, those letters are getting pretty messy. Sine of 60 divided by sine of 30. I'm thinking Luke is right. It'd be better just let's calculate what that is and put a number in there. Okay, so sine of 60 divided by the sine of 30. Okay, so I get 1.73. Okay, so V2 is equal to 1.73 times whatever V1 is. Okay, so now I can take that and I can plug that in up here. Wherever I see a V2 up here, I can replace it with what I know V2 is equal to. All right, so my whiteboard has run out of space as usual. So let me clear some space over here so I can get some work done over here. Don't really need the picture anymore. Okay, I wish there was a faster way to erase large spaces on the whiteboard. There probably is. If you guys ever see another teacher find out a better way to do it, please tell me what that is. Okay, so now I'm going to take this equation right here. So I'm going to say that V initial, and since we're putting in numbers, let's go ahead and put in numbers. So V initial, if I remember right, was 4. Actually, it was 4.0, so we had 2 sig figs, but okay. So that's equal to V1 times the cosine of 60. So let me go ahead and put that in. Cosine of 60. Oh, yeah, so kind of 1/2. I should have known that. Okay, so V1 times 0.5 plus V2, which we know is 1.73 times V1, times the cosine of 30. Okay, so what is 1.73 times the cosine of 30? Okay, so what I get then is 4 equals 0.5 times V1 plus 1.49 times V1. So that's 4 equals 1 point. So if I combine 0.5 and 1.49, so we're 4 then equals 1.99 times V1. So V1 then equals 4 divided by 1.99. Okay, so I get the V1 equals 2.01. All right, and then how do I get V2? Well, V2 is just equal to, well, 1.73 times that. So let's take that times 1.73. And so I get V2 must equal 3.477. So now if I round off, so if, let's see, I'm allowed, looks like 2 sig figs is what I'm allowed. So that means that V1 equals 2.0 and V2 equals 3.5. Okay, and hopefully that matches what we had before. If not, that's going to be pretty embarrassing. Ah, okay, hey, what do you know? It does match. Okay, so there's problem number 24. Okay, so Sid is asking, is it linear because the balls aren't spinning? Yes, and that is a very important point. In the real world, if you guys have played billiards, you know that someone who's a really master billiards player, they can put some spin on the balls. And so the balls are going to have some angular momentum, and we would need to take that into account. But
There's
since we
actually a person who was able to make a billiard ball spin so quickly that he was able to make it do a parabola and get into a hole from the
wow,
opposite end.
very cool. Yeah. But we're not gonna deal with angular momentum. So we're assuming that the balls are not spinning. But Sid, you are right. In the real world, we would have to worry about that. So when you take the U of U physics class next year, and I hope that you all do, you'll learn how to do angular momentum at that point. Okay, so that's where I'd like to cut it off here. I want to make sure that we have time for the new material. At the end of the period, if we have some time left over and you want to ask some more questions about last night's homework, I'm good with that. So let's go ahead and just jump into the new material. All right, so we are starting into chapter 10 today. Chapter 10 deals with energy and work. And that's what we're going to talk about tonight. And then next time we meet, we'll talk about simple machines. But tonight, the focus is on energy and work. Now, energy and work, those are two words that you have been using all of your life. I'm sure that many times you have used the word energy and you have used the word work. Do you understand what energy really is? And when I say what it really is, I mean the way that a physicist defines energy. So anybody want to try to unmute yourself here and tell us, how would a physicist define energy?
However much energy it takes to make an object do something you want it to.
Okay, so energy is the ability to make an object do something you want it to. Okay, all right. Could we be a little more specific about what it is that we might want the object to do? Okay, Luke is suggesting that energy is the ability to do work. Yes, that is exactly the way that energy is defined. So let me just open up a whiteboard so we can write it. Just the act of writing helps reinforce it. Okay, so what we're going to do then is we're going to say that energy, and then I'm going to use this symbol that you guys have seen many times before, and you will see many times again, is defined as, okay, the ability to do work. So when I wake up in the morning, if I'm really feeling tired or maybe I'm feeling sick, I say, oh, I just can't go into work today. I just don't have the ability to do work. And so if you believe the ads that they put on TV about those little energy drinks, I'm sure you've seen those ads, you know, they would have you believe that if you drink these little overpriced little bottles of their special liquid, then it will give you the ability to work. You know, you'll give you energy. It'll give you the ability to do work. Okay, so now we know what energy is, or do we? Okay, because what is work? If you don't really understand what work is, then you don't really understand what energy is. Okay, so what is work? Let's suppose that I am let's suppose that my name is Carter Jensen. He's my favorite guy to pick on. Okay, so he's a mathematician, right? So if a mathematician is working, how do you know that they're working? Well, I mean, if I'm sitting here and I'm thinking about some mathematical proof, Mr. Jensen gets paid to do math, right? So let's suppose he's just sitting in his chair thinking. Is he really doing work? Now, he claims he is. And in fact, he gets a paycheck for doing it. But is he really doing work the way that a physicist defines work? Okay.
Well, it's kind of debatable, I guess, because there is energy being used in the brain, but it's not being seen physically, so it's debatable.
Yeah, if there's no physical manifestation, then a physicist would say that he's not doing any work. Lila, did you have a comment?
That work would be more in the sense of motion, and so I think that's kind of partially why. I
Aha.
don't know, just an idea.
Okay, so Lila is suggesting that there needs to be some motion involved. Okay, so I'm thinking she's onto something, and the example that I like to use is this one. You guys hopefully are seeing a picture of Atlas holding up the world. So let's suppose that that's his job. That's what Atlas gets paid to do, is to hold up the world. So 8 hours every day, he stands there holding up the world, and the world is pretty darn heavy. So his arms are going to get really tired. So at the end of his shift, he hands off the world to somebody else, somebody who's working the swing shift, and he punches out the time clock and he goes home. And when he walks in the door, he kisses his wife and she says, "How was work today, honey?" What do you think? Did Atlas do work? I mean, his arms are going to be really tired. And so you can understand why Atlas would say, "Yeah, I really did a lot of work today." But Lila seems to imply that Atlas didn't actually do any work, because Lila is saying that no motion occurred. And it looks like Cora agrees. I see that Cora has typed into the chat box here. Cora is suggesting that work is force times distance, so that if nothing moved, then no work was done. So it sounds like what you guys are suggesting is that if Atlas had been smart, what he could have done is he could have taken, you know, instead of spending 8 hours holding the world up above his head and getting his arms tired, he could have just set the world on the table, and then he could have spent 8 hours sitting there reading a magazine, and you know, the world doesn't hit the ground, right? So his job gets done. So if your job can be replaced by a table, then you're not really doing work, at least not the way that physicists define work. Okay, so what Cora typed in the chat box is 100% right, is that in order for work to be done, you need to exert a force, and that force needs to result in something moving. All right, so let's go back to our whiteboard here. So then now we're going to define what work is. So work is defined as a force acting on some object multiplied by the distance that object moved as a result of the force that was acting on it. Okay, so you need to have both. You need to have force, and you also need to have distance. Okay, so in your homework tonight, the first couple of problems are going to be ridiculously easy. They're just going to say, okay, I'm pushing on some object with some force. Oh, let's say that it's 25 newtons of force. And as a result of that, the object moves some distance, and I keep that force acting on the object the whole time that it's moving. Okay, and so that means that there must be some force opposing it. Like, so a good example here is, let's suppose I have a box sitting on the table and there is friction, right? So when I push on that box, I find that the amount of force that I need to exert in order to overcome friction and have that box move with a constant velocity, I find that it's 25 newtons. So what that means is that friction is resisting me with the force that's equal to that. Okay, so then I push the box and I push it a total distance. The distance I push it, let's say, is 3 meters. So in your homework tonight, they're going to say, well, how much work did you do? Well, okay, so work is force times distance. So 25 is the force. So 25 times 3 is 75. So the answer is 75, whatever units it is we use to measure work in. Okay. Well, that brings up the question then, what are the units we use to measure work in? And so remember when we did this with momentum, when we said the momentum was equal to mass times velocity, the units for mass are kilograms, the units for velocity were meters per second. So therefore the units for momentum worked out to be kilogram meters per second. Well, we could do the same thing here. The units for force are newtons. The units for distance are meters. So then we could say that the answer is 75 Newton meters. And I could not mark that wrong. That would be good. But now here's a case where scientists, they did say to themselves, well, we're not going to just leave it as a Newton meter. Let's give it a name. And the name that they gave it is the name of the scientist who was one of the leaders in working with this type of thing. His last name was Joule. And so they decided, okay, instead of calling it a Newton meter, we're going to call it a joule. So 75 joules of work is what we're done, is what we're going to call it. Now, if energy is the ability to do work, so then if we did 75 joules of work, that means we must have used up 75 joules of energy, right? So it turns out that the units for energy are the same as the units for work, because, you know, if you did 75 joules of work, you must have used up 75 joules worth of energy. All right, so this is going to be pretty straightforward for the first couple of problems in your homework, but it gets more interesting. Because that's too easy. I don't want you guys to be bored by doing problems that are too easy. All right, so let's make it more interesting by saying that here's the block. But the force that we're going to use when we push on this block, instead of being parallel to the motion of the block, okay, so let's work with vectors here. So, and I like my vectors to be thicker, so let's do that. Okay, so let's say that this is my displacement vector. Okay, and so that maybe it's 3 meters, maybe it's something else. That's my displacement vector. Now, when we did it before, my force vector was parallel to the displacement vector, but that was too easy. So what I'm going to do then is I'm going to say, well, I want my force vector to be off at an angle. So here's my force vector at some angle theta, and I'm going to use this as the measure for my angle, because when you're dealing with vectors that are pointing at different angles and you want to know what's the angle, even though the force is acting up here, you know how I like to draw my force vectors so that the tail of the arrow is on the is right here. So all of the arrows have their tails at the same place. Okay, so I'm going to put my force vector down there, even though some of you might say, well, you're pushing up here. Well, it doesn't matter, right? Okay, so the angle here is theta. And so that's the angle here. So now the question becomes, how much work am I doing? Okay, well, we've got a funky vector. And so what do we always do with funky vectors? We defuncify them. We break them up into their components. So tell you what, I don't want my picture to be too cluttered. Let's go back to this picture up here. Okay, so if this is my force vector here, okay, and it's funky, so I'm going to break it up into its components. So I'm going to have this component and I'm going to have that component. And those two red arrows do the same job that one black arrow does, but they do it in a non-funky way. And so if this here is theta, then our vertical component here is going to be F times the sine of theta. And my horizontal component is going to be F times the cosine of theta. So I don't need my black vector anymore. I've replaced him with his components. Okay, now here's the question. How much work is the vertical component doing? Okay, so I've got a force that's acting in the vertical direction. Is the object moving in the vertical direction? Answer, no. So what we have here is exactly the same situation as Atlas holding up the world. Okay, this component is sitting there pushing really hard, but it is not doing any work because the object is not moving in that direction. So this guy does no work at all. The only work that's done is this guy, and he's parallel to the displacement. And so, you know, work equals force times distance, where this force is the force that's parallel to the displacement. Okay, so that's the x component. So the work then is equal this component, which is F times the cosine of theta, times this displacement, which is D. Okay, so the work then, F d cos theta, that is a better way to remember it. Okay. And now when you look in the book, you're going to find that in the book, they prefer to call it FD times the cosine of theta. That's fine. Yeah, they can rearrange. You can swap places there. 3 times 4 is the same thing as 4 times 3. So if they want to change the order, okay, fine. So work equals F times D times the cosine of theta. That's the one to remember. Okay. And when I say F, what I really mean is I really mean the magnitude of the force vector. Okay. And when I say D, what I really mean is the magnitude of the displacement vector. And then when I say cos theta, the theta that I mean is the theta that if I were to take my two vectors, if I were to take my force vector and my displacement vector and put them so that their tails are in the same place, then the theta that I want is the theta that's the one in between those two vectors. Okay, so this that you see at the bottom here, this is really the best way to write it. It's the magnitude of the force vector times the magnitude of the displacement vector times the cosine of the angle in between. Okay, so in your homework tonight, the second group of problems you're going to have are going to be ones like this. And I trust that you'll be able to do them without any problem at all. Okay. All right. So now we know what energy is. We know what work is. Now, let's talk about different types of energy. And so the first type of energy that I want to deal with is the energy of a moving body. So imagine you've got a car driving down the road. It's moving, and tell you what, let me open up a whiteboard so I can draw a picture here. Okay, so here's the road. Here's some car that's moving down the road. It's moving this velocity here. And now, in order to get the car moving, you had to put your foot on the gas. But now that it's moving, let's say that you've taken your foot off the gas. And let's assume that there's no friction. And there's no air resistance. And so this is the totally idealized case. So once the car gets moving, if there's no friction, no air resistance, you should be able to take your foot off the gas and the car will just keep on moving at a constant speed. Okay. But there's a crate sitting in the road in front of the car. And there is friction here. So yes, there is friction between the bottom of the crate and the road. Okay, so when the car hits the crate, is the car going to be able to push the crate? Yes. And now the crate is going to push back, Newton's third law. Okay, so if the car is exerting a force on the crate is going to exert a force on the car. And so eventually the car is going to lose its momentum and it's going to come to a stop. All right, so if this is the before picture, let me switch to red ink for my after picture. So now the crate has now moved some distance d, and here's the car in contact with the crate. Okay, and so then eventually they come to a stop now. So has the car exerted a force on the crate? Yes. Did the crate move as a result of that? Yes. So did the car do some work? Yes. So that means that this moving car, before it hit the crate, it had the ability to do work, therefore it had energy. And so we have a special name for that. If you have energy as a result of your motion, we're going to call that kinetic energy. Okay. Now, I'm sure you guys can understand that the faster the car goes, the more energy it's going to have. But also, the more mass the car has, the more energy it's going to have. So, sounds to me like momentum. So it almost sounds as if however much momentum a car has, that's equal to how much kinetic energy it has. So let me ask, do you guys agree? So I want you to type yes into the chat box if you agree that the momentum that the car has is equal to its kinetic energy. I'd like you to type no into the chat box if you disagree. Okay, so I need to see some answers here. Yes means you agree that kinetic energy and momentum are the same. No means that you disagree. All right, I'm seeing roughly equal numbers of yeses and nos. All right. All right, so Zamara, you were one of the people that said no. Can you unmute yourself and tell us why? Why did you say no?
I feel like they're just two different things. They're just not the same.
But doesn't it make sense? I mean, the more mass you have, the more work you can do. The more velocity you have, the more work you can do. So, I mean, intuitively, at a gut level, it makes sense. But you're suspicious. Why are you suspicious?
I don't think they can be the same, but maybe they can.
Maybe they could. Let's see, who else said no? Let's see, Cora. Cora said no. Why did you say no, Cora?
I don't have an exact reason, but momentum and energy are measured with different units for one.
Ah, okay, good point. Different units, that's a good clue. Okay, and I'm willing to bet that several of the rest of you, the reason that you said no is simply because Mr. Hendricks is the one who's asking the question. I mean, generally when I do this, the response is, they say, well, if any other teacher had asked this question, I'd say yes. But if Mr. Hendricks is asking it, there must be a trick. Okay, and it turns out that momentum is not, in fact, equal to kinetic energy. But for many years, people thought that it was. They could have easily answered that question if they had just done a very simple experiment, an experiment that we are going to do right now. Okay, so here's the box, here's the road. Okay, now I don't have a car handy, but I do have a battery handy. Okay, so let's have this rolling battery. That can be the car. All right, so when the car hits the box, it's going to push the box. Now there is friction, and so what's going to happen is it's going to come to a stop. So if I do an experiment where I send in my car or my battery, if I send it in with a certain speed and I measure how far did it push the box, okay? And then I come and I do the experiment again, where the second time I give it twice as much speed as I gave it before, okay? And I measure how far did it move the box. And you'll see that when I gave it more speed, it did in fact move the box faster or move the box farther, right? Okay, so let's draw a picture of this. Okay. All right, so let's say that I've got so here's my car. And let's just make it be a simple car like that. And here's my box. So the car has a mass m and is moving at a velocity v. Now, when it hits the box and it tries to move the box, okay, it has to overcome the force of friction. And then let's say that it moves it some distance d here, okay? So the work done is equal to force times the distance, and that's equal to however much kinetic energy it had, right? So if it was true that kinetic energy was mv, then that means that the work that it does would be proportional to mv. So we're claiming, so let me write here that the claim is that the kinetic energy is equal to mv. Now this is a claim, which by the way is not true. So let me just put a question mark above that equal sign. Okay, so if that was true, then you notice that the m here does not have m, it's not m squared, it's not the square root of m, it's just m. Same with the v, that's not the square root of v, it's not v squared, it's just v. So if this was true, then if I were to replace v with twice v, then the amount of work that I do should be twice as much work. So that means that if I do this experiment a second time where my second velocity is equal to twice what my initial velocity was, then that means that the box should get moved twice as far. Okay. So when they actually did the experiments here, okay, so they do it the first time with the car moving at a certain velocity, and they measure how far the box moved. And so then the second time they have the car, so it's moving twice as fast as it was the first time. And what they find is that when the car is moving twice as fast, it doesn't move the box twice as far. It moves the box 4 times as far. And then when they do it again, where the car is moving 3 times as fast, it doesn't move the box 3 times as far. It moves the box 9 times as far. So what does that tell you about this equation here? Okay, what it tells you is that the work done, which in this case is equal to the kinetic energy, it tells you that it's proportional to v squared, not proportional to v. And then now we should, in order to be complete, we should also do the same thing with the mass. We should do the experiments once with a car that has a mass m, and then we should do it again with a car that has a mass twice as much. So when they did that experiment, they found that replacing the car with a car that has twice as mass, that did in fact make the box move twice as far. So that tells you that the kinetic energy is proportional to m, but for v, it's not proportional to v, it's proportional to v squared. So that means that the kinetic energy is proportional to m times v squared. Now, I don't like proportional signs, I like equal signs. So if I want to replace that proportional sign with an equal sign, what do I have to add that I didn't have in there before? I have to add a constant. So some constant times m times v squared. And how do I know what the value of that constant is? Well, I can determine that experimentally. All right, so what I can do is I can take a car that has a mass that I know what it is, and let's make it easy. Let's assume that the mass is 1 kilogram. All right, and I can have it be moving at any speed that I want, and I can measure what that speed is. Let's make it easy. Let's assume that the velocity is 1 meter per second. And then what I can do is I can calculate how much work does it do. And I know that that work is going to equal however much kinetic energy it had. And I can measure that. Because if I know the mass of the box, and I know what the coefficient of friction is, okay, and I know the distance, I can actually come up with a number for how much work it did, which means then I knew how much kinetic energy it has. So when the scientists do this with a mass that's 1 kilogram and a velocity that's 1 meter per second, what they find is that the work that's done is 1/2 of a joule. Okay, so what does that tell you about the value for K? Well, if M is 1 and V is 1, the only way that you can get an answer of 1/2 is if K is equal to 1/2. So this is something that we've experimentally determined. Now, some of you might say, well, if you did it experimentally, then you can't really be sure that it's 1/2. You know, it might be, you know, depending on how good your equipment is, you know, it might be that it's somewhere between 0.49 and 0.51. And if you do it better with better quality equipment, then you can say, okay, then it's between 0.4999 and 0.50001. Okay, so as long as you're experimentally determining it, you cannot say with confidence that it's exactly 1/2. Okay, but you can certainly say that it's really, really close to 1/2. Now, later on, we're going to do some work where we will prove that it turns out it is exactly 1/2. Okay, but we don't yet know enough physics to do that. So for right now, let's just say that experimentally we've determined that it's 1/2. Okay, so somebody just sent me a private message saying, what does K represent? Well, K is the proportionality constant. Whenever you have something where you say that the thing on the left is proportional to the thing on the right, and then you say, well, I don't like proportional signs, I like equal signs, then whenever you change that proportional sign to an equal sign, you have to put a proportionality constant in there, because you can't say that kinetic energy is equal to mv squared. All you can do is you can say it's proportional to mv squared. And so there might be some number in front of there. And so you have to experimentally determine what that number is. Okay, so when we do this experimentally, what we've determined is the kinetic energy is equal to some number, which is approximately equal to 1/2 times mv squared. And later on, we're going to prove that it's not just approximate, it actually is exactly 1/2. Okay. All right, so in your homework tonight, they're going to give you some problems like that. They're going to say, I got some object that's got a mass m moving at speed v. How much kinetic energy does it have? Well, this is how you do it. Pretty straightforward. Okay, now let's make it a little more interesting. Let's do a problem where you're going to have to pull in some things that we learned a couple weeks or maybe a couple months back, like you're going to see in the homework tonight. Let's assume that I have a box and it has a mass m where m is some known number. Let's say that it's 3.2 kilograms. And it's sitting on a floor where the floor is not frictionless. And it has a coefficient of friction of, oh, I don't know, let's say 0.46. And you know that the coefficient of friction is a unitless number. Okay, so let's say that the car comes along, and now the car is frictionless and there's no air resistance. So let's say that the car has a mass of, let's say that it's 6.2 kilograms, and it's moving at a speed of 1.8 meters per second. So the car is going to hit the box, and let's say they stick together, and it's going to push this box some distance. So I want to know how far is it going to be able to push the box before everything comes to a stop. Okay. That is a problem that you can do. You'll have to think about it for a little while, but you have, based on what we've just said over the last several minutes, you now have the tools that you need to solve this problem. So how would we do it? Well, first thing we're going to recognize is that the kinetic energy that the car has, that's equal to the work that it's going to be able to do. Right? Well, how much kinetic energy does it have? Well, 1/2 times m times v squared. Now, what is the work that it's going to be able to do? Well, work is defined as the force times the distance. And distance is what we're looking for. And we know the mass and we know the velocity, but rats, we don't know the force. So if only we could figure out the force, then we'd be in good shape. Well, as the thing is moving, so let's say that the box is here in the middle. Okay, so let's do a free body diagram. And I like my forces to be fat, so let me fix it. Okay, so we got mg going down. We got the normal force going up. The car is pushing the box. So here's the force of the car pushing on the box, but friction is opposing that. So here's the force of friction opposing that. And let's assume that it's moving the box at constant speed. And so that means that the force that the car is exerting is equal to the force of friction. So this force here, that's the force of the car pushing on the box. That force is equal to the force of friction. And now I realize it's been a while, but hopefully you guys remember, what is force of friction? Well, that's mu times the normal force. What is the normal force? Well, here's the normal force here. And what do you see that's equal and opposite to it? Mg. Now, if we were on a hill, then it would be mg cos theta, but we're not on a hill. So it's mu times mg. So let's take this and move it down here. So what we got then is 1/2 mv squared equals the force, which we now know is mu times m times g, times the distance, which is d. Notice the mass of the car cancels out. Oh, sorry, no, does not cancel out. These are not the same, okay? This m here is the mass of the car. This m here is the mass of the box. So in order to solve this, we're going to need to know what the mass of the box is. So let's say the mass of the box is, oh, I don't know, let's say 2.7 kilograms. Just, I'm making up numbers. Okay, so from this point on, it's no longer a physics problem. Now it's just a math problem. We know the mass of the car. We know what the velocity of the car was before it hit the box. We know what mu is. We know what the mass of the box is. We know what planet we're on, therefore we know what g is. So I'm thinking from this point on, heck, even Mr. Jensen could solve it from here, right? So do we need to bother from here, or can we just say from this point on, it's no longer a physics problem, now it's just a math problem, and you're good at math, right? Okay. So how are we doing here? Does that make sense, what we just did? Okay, good. All right, now, there is one last thing I need to tell you about, just really briefly, before I let you type by into the chat box. When you look in your book, because I know that you always read the book before you do the homework, right? So when you look on your book, in fact, if you look on page 259, they're going to give you something that they call the work energy theorem, I think is what they call it. So let me just open up a whiteboard here. So they're going to claim something that we've already used. They say that the work that you do is equal to the kinetic energy, which is something we just got through saying. And they're gonna give this an official name. They're gonna call it the work kinetic energy theorem. And they're gonna make it look as if this is always true. But I need to warn you, this is not always true, because there are different types of energy besides just kinetic energy. Some of you may have heard about something called potential energy. Some of you may know that there's electrical energy, there's magnetic energy, there's chemical energy. If there's a spring involved, then there's something called elastic energy. So there are lots of different types of energy. So the work is not always equal to the kinetic energy. It's only equal to the kinetic energy if there are no other forms of energy involved. Okay. In fact, when you look in your book, don't be surprised if you see that a previous student has gone ahead and written in the book, because I asked them to do this. I asked them to get out their pencil and write in the book and say that this is only true if there are no other forms of energy involved. Okay. If there are, then that's going to mess things up. But for tonight's homework, there will not be any other forms of energy involved. And so for tonight's homework, that'll be, you can go ahead and assume that however much work is done, that's how much kinetic energy did the work. So then I guess the only thing that we need now is just to know what the homework is. So here it is, homework 10A. Make sure you read the first part of the chapter before you do the homework. And then I want you to do problems 1 through 8. And of course, also don't forget to take the quiz. Taking the homework quiz is really important. Okay, so I just got a question asked in the chat box. You're wondering, will you not be able to see your answers on the midterm? Okay, so you want me to change this Canvas so that you can look on Canvas? Yeah, I can do that. Okay, so I'll do that. As soon as we log off here, what I'll do is I'll go into Canvas and I'll reset Canvas so that when you go in to look at the midterm, it will show you which problems you got wrong. In fact, I thought that I already had it set that way, but maybe I forgot to. Now, it won't tell you what the right answer is, but it will tell you what ones you got wrong. Okay, I think we're good then. So if you guys want to type bye into the chat box, remember that the period is not over. We still have 20 minutes left. So please use that time to work on physics. Don't do other stuff. And I'm going to go ahead and turn off the recording now. So if you had a question that you didn't want to ask because you knew it was being recorded, now is your time to do that.